You ever open up a spreadsheet, maybe one of those massive corporate ones with just thousands of rows and columns, and you just stare at it?
Oh, absolutely.
Like it's an endless wall of numbers. It's dense. It's chaotic. And honestly, your brain just sort of shuts down because it can't find a pattern in all that noise.
It's a very human reaction, honestly. I mean, we just aren't wired to process millions of raw data points simultaneously. You look at a grid of sales figures or user clicks, you'll just see static.
Right. But what if there was a way to put on a pair of glasses, like a mathematical decoder ring, that suddenly made all the hidden patterns in that spreadsheet just pop out in 3D?
That is the dream, right?
Exactly. And today, we are extracting the core insights from this really fascinating visual guide called Matrix Factorization Blueprints. And the mission for this deep dive is to decode that hidden underlying geometry of data. We're going to look at the single mathematical bridge connecting pure linear algebra to the applied machine learning that powers, well, so much of our daily lives.
Yeah, everything from movie recommendations to how computers understand language.
Right. And what I love about this document is how it takes something visually intimidating and turns it into this massive aha moment.
It really is a fundamental structural concept because, so much of what we call artificial intelligence or machine learning is often presented to people as this impossibly complex black box.
Like magic.
Exactly, like magic. But this blueprint breaks it down and shows that beneath all the highly specialized applications, there is just one profound mathematical truth being applied in different ways.
Okay, but before we can understand how modern algorithms learn, we first have to understand the pure ideal mathematical theory that started it all, right?
We do. We have to look at the foundation.
And to do that, we have to look at the fundamental equation of this entire deep dive. So,
Yeah.
okay, let's unpack this. The equation is A is approximately equal to U times sigma times V transpose.
I know, it sounds like total alphabet soup.
Yeah, it really does. Let's ground this for everyone listening.
It looks intimidating on a whiteboard, I admit, but it's incredibly elegant once you isolate the pieces. So, let's start with A. That is your raw data matrix, that massive, messy spreadsheet you're just talking
The
about.
wall of numbers.
The wall of numbers, exactly. Now, decomposition algorithms act as a mathematical prism. Think about shining a complex, messy beam of white light into a glass prism.
Okay, like the Pink Floyd album cover.
Exactly like that. The prism splits that surface-level white light into its fundamental underlying colors.
So this equation takes our messy data beam, our A, and splits it into three distinct interpretable pieces.
Right. It splits A into three latent structures. First, you have U, which represents the row or user factors.
Okay.
Then you have sigma, which is a diagonal matrix containing the singular values. Think of these singular values as the weights, like the energy or importance of each underlying factor.
Got it.
And finally, V transpose, which holds the column or item factors.
The blueprint talks about this in the realm of pure linear algebra through a concept called exact SVD, or singular value decomposition. And it says the math guarantees that literally any matrix can be factored exactly using these orthogonal bases for the row and column spaces. But let's pause there because orthogonal bases is heavy textbook jargon.
It is, yeah.
How should we actually visualize that?
Well, think about physical space. If you walk strictly north, your altitude doesn't change. North and up are entirely independent directions.
Right, they don't affect each other.
Exactly. In math, we call that orthogonal. When we say the algorithm finds an orthogonal basis, it means it's finding dimensions in the data that don't overlap or influence each other at all.
Yeah.
It's isolating the pure independent traits of the data.
It's like a perfect mathematical reconstruction of the original spreadsheet. But wait, if the data is just a giant block of numbers, how does a mathematical prism know what constitutes a user trait versus an item trait?
What's fascinating here is that in the ideal world of pure math, it doesn't know. It has literally no concept of what a human user is, or what a movie is, or what a shopping cart is.
That's just numbers.
Right. It is ruthlessly seeking the mathematical absolute truth of the space. It is just finding the natural dimensions where the numbers vary the most, completely blind to the real-world labels we attach to them.
It just finds the structural truth.
Hmm.
But of course, that perfect exact math exists in a vacuum. Because while the ideal math is flawless, real-world data is practically suffocating under useless noise.
Yeah, pure mathematical replication is actually a liability in the real world. Think about it. If you perfectly memorize every detail of a noisy room, you're memorizing the static along with the music.
Oh, that makes sense.
So we have to transition from perfectly replicating data to intentionally throwing parts of it away.
And this brings us to the truncation slicer and something called the Eckhart-Young theorem. The blueprint explains that to get the optimal lower rank approximation of a matrix, meaning like a simpler version of your data that is as close to the original as mathematically possible, you discard the smallest singular values.
Yes.
You literally chop off the bottom of the sigma matrix we talked about earlier.
It's an aggressive but completely necessary filter. Those singular values in sigma are ordered by importance. The highest values contain the core energy of the data, and mathematicians measure this energy using something called the Frobenius norm.
Okay, let's define Frobenius norm for a second. The document mentions it a lot, but what is it practically?
Okay, imagine your data matrix is a physical object. The Frobenius norm is essentially measuring the total volume or mass of that object.
Like how heavy it is.
Yeah, it calculates the overall mathematical weight of all the numbers combined. When you look at the singular values, the top ones carry almost all of that weight.
And the lowest values.
That's almost always just random noise or redundant information that isn't actually helping you understand the true shape of the data.
The blueprint gives this incredible specific example. It shows a matrix, and by extracting just the first pair of singular vectors with a dominant singular value of 50.02, it captures so much of the variance that the residual matrix, the leftover junk after you subtract the approximation, has a Frobenius norm of just about 1.
Which is incredibly small.
It's practically nothing. So
Yeah.
is this essentially like summarizing a massive 500-page fantasy novel into a 5-page cheat sheet? You lose the minor, noisy subplots, the tavern keeper's backstory, the detailed description of the trees, but the dominant energy, the core story, remains perfectly intact and is just much easier to process.
Yes, exactly. I mean, it's less about summarizing text and more about turning down the static on a radio dial so the actual broadcast comes through clear, but your intuition is spot on.
Right, you lose the texture of the tavern keeper's backstory, but you retain the structural fact that the hero needs to defeat the dragon.
Exactly. For a machine trying to process millions of complex data points, that distilled cheat sheet is infinitely more valuable than the noisy original. It zeroes in on the signal.
Okay, so truncation works beautifully when you have a noisy but complete set of data, like a fully written 500-page book. But that perfect, complete data rarely exists out in the wild.
Almost never.
And this limitation literally forced machine learning to evolve, didn't it? The math collided with reality in the form of extreme sparsity.
This is the massive hurdle of modern applied machine learning. Pure linear algebra, the beautiful exact SVD we just outlined, makes one non-negotiable demand. The matrix must be complete.
Every single cell in that spreadsheet needs a number.
Every single one.
But real-world data is like a Swiss cheese of missing information.
Oh, okay.
I mean, think about your Netflix account.
Yeah.
Netflix has thousands and thousands of movies. You, as a user, have maybe rated, 10 of them?
If that, yeah. So your specific row in that giant user item matrix is 99.9% completely blank. Or consider sensor logs in an Internet of Things network where devices constantly drop Wi-Fi connections. The data isn't just noisy, it's fundamentally hollow.
And traditional analytic SVD completely breaks down here. It cannot compute on an incomplete matrix. If there are blanks, the pure math just throws its hands up and crashes.
It cannot function. SVD is a top-down analytical process. It needs the whole picture to perform the calculation. When the picture is 99% empty space, a fundamental evolutionary leap is required. We had to move away from pure analytical math and pivot to optimization.
Here's where it gets really interesting. To handle this missing data, Matrix Factorization frames the problem entirely differently. Instead of trying to mathematically solve the whole matrix at once from the top down, it learns the latent factors are U and V transposed. There's something called stochastic gradient descent, or SGD.
Right.
It computes the errors, the function J, only over the entries we actually observed.
This is the massive paradigm shift from traditional statistics to modern machine learning. You aren't deriving the answer. You are guessing the answer, seeing how wrong you are on the few data points you actually have, adjusting your parameters slightly, and then repeating the process.
But wait, I need to make sure I'm wrapping my head around this. If 99% of my Netflix matrix is blank, isn't the algorithm just making wild guesses based on almost no data?
It sounds like it, sure.
How is that statistically sound? We just give up on solving the equation and have a computer guess and check its way to an answer based on 5 movie ratings.
Well, it sounds like wild guessing, but it's actually highly structured navigation. Picture a massive three-dimensional topographical map of hills and valleys, where the valleys represent the lowest possible error in our predictions.
Okay, a topographical map.
Stochastic gradient descent is like being dropped onto that landscape blindfolded. You can't see the whole map, that would be analytical math, but you can feel the slope of the ground right under your feet.
You feel which way is downhill.
Exactly. You take a step in the steepest downward direction, you check your error again, feel the slope, and take another step.
Oh, wow.
Even though you are only looking at the tiny fraction of movies you did rate, the algorithm uses those known points to continuously step downhill until it finds a set of user vectors and movie vectors that perfectly explain your existing ratings.
And once it learns those latent vectors for you and the movies, it just multiplies them together to predict what you would rate the movies you haven't seen.
Precisely. It fills in the blanks.
That is wild. Because stochastic gradient descent untethered us from needing a perfect, complete grid of numbers. Researchers suddenly realized they could feed any complete data into this engine.
Any sparse data, yeah.
And this realization created the factorization family tree, applying this exact same geometric engine to wildly different real-world problems.
It became a universal skeleton key. Recommender systems, specifically weighted matrix factorization, are the most direct application. This is predicting that missing 4.5-star rating via the dot product of your user row and the movie's item column.
The blueprint points out a crucial mechanical detail for recommenders, though: negative sampling. Why is that necessary?
Because of how we interact with the internet, most of our data is implicit feedback.
Like what we click on, not what we explicitly rate out of 5 stars.
Exactly. If a system only looks at the videos you clicked on, the math starts to assume you just love everything in the database.
Right, because there's no negative data.
Negative sampling artificially injects zeros into the math for things you ignored. It forces the gradient descent to learn your boundaries, to understand what you actively dislike, which really grounds the geometry.
That makes total sense.
Oh.
Now, let's look at the next branch of the family tree, factorization machines. The document says this extends the concept beyond just 2 dimensions into something called sparse regression. We probably need to define that.
Sure. Sparse regression deals with data sets where you have an enormous number of possible variables, but for any single event, almost all of them are 0. Imagine trying to predict what ad a user will click. You have millions of variables: the user's ID, the time of day, the website they are on, the specific device they're using, the last 3 ads they saw.
That's a lot of variables.
But for a single click, 99.9% of those variables are empty or sparse.
And traditional models struggle with that because they try to calculate a weight for every single variable independently.
And they fail completely when trying to calculate the interactions between those sparse variables.
Right.
Factorization machines solve this by assigning a latent vector to every single feature. It doesn't just look at time of day and user ID separately, it models the pairwise interactions between their vectors, effortlessly capturing complex relationships, even when the data grid is mostly empty.
It scales the geometry. But the application that really changes how you see the world is natural language processing, specifically the glove algorithm. Language, it turns out, is just another sparse matrix.
It is. Think about how a computer could possibly understand the concept of a word. It can't read a dictionary. But if you take a massive corpus of text, say all of Wikipedia, and you just count how often words appear near each other, you create a massive grid.
A co-occurrence matrix.
Yes. You count how often the word ice appears within 10 words of solid versus how often it appears near gas. You end up with an impossibly large, mostly empty spreadsheet of numbers representing these relationships.
And when Glove factorizes that massive sparse matrix, it extracts latent semantic vectors for every word. It literally maps human language into computable geometric space.
It does.
The blueprint highlights the famous mathematical proof of this. If you take the geometric vector the algorithm learned for king, subtract the vector for man, and add the vector for woman, the resulting coordinate in geometric space is the exact vector for queen.
It's a beautiful result.
I need you to explain how the gradient descent actually makes that happen, though.
It comes back to the topography we discussed earlier. Because the words king and man frequently appear near similar contextual words in all of Wikipedia, the gradient descent continuously pushes their vectors closer together to minimize the error.
Okay, that tracks.
Over billions of steps, the algorithm mathematically isolates the distance between words. It learns that the specific distance and direction separating man from king is the exact same geometric distance and direction that separates woman from queen.
Wow.
That distance essentially becomes the mathematical representation of royalty or gender. We turned human semantics into pure distance and direction.
It maps meaning. And we see this same mapping in graph networks, too. Social networks, computer networks, supply chains.
The underlying data structure there is called an adjacency matrix.
Let's visualize that for the listener.
Yeah.
Imagine a grid with all your friends' names along the top and those same names down the side. If two people are friends, you put a 1 in the intersecting box. If they aren't, you put a 0. That's an adjacency matrix.
And just like the Netflix matrix or the Wikipedia matrix, it is mostly empty.
Right, because I'm not friends with everyone in the world.
Exactly. When you factorize that adjacency matrix, it reveals latent communities. It geometrically groups nodes that share structural similarities. The algorithm can look at the vectors and see that two people are incredibly close in geometric space, even if there isn't a 1 connecting them yet.
Oh, it's the people you may know feature.
That's exactly how it predicts future edge connections, or links, between nodes, by looking at their vector proximity.
It's like finding out that the engine powering your car, the compressor in your refrigerator, and the processor in your laptop are all secretly the exact same machine, just tuned differently. All these highly specialized tasks, recommending a movie, understanding the nuance of the word queen, suggesting a friend on a social network, they seem completely unrelated on the surface, but they're actually running on the exact same geometric engine.
If we connect this to the bigger picture, it really speaks to the universal nature of the math. You take the same core principle, apply it to a different data set, and solve a completely different problem.
We've seen how changing the input data changes the machine learning output. But what happens if we change the rules of the math itself? This is the final realization of the document, the universal factorization blueprint.
We've been talking about changing the ingredients. Now we are talking about changing the recipe. The universal blueprint relies on that single structural concept we unpacked at the very beginning. A is approximately equal to U times V transpose.
The exact same equation from the start.
The very same. By simply altering the objective function, or most crucially adding strict mathematical constraints, we fundamentally change the behavior of the model.
So let's look at the k-means clustering example from the blueprint to see how constraints change the game.
Well, in everything we've discussed so far, recommenders, NLP, graphs, the latent matrices U and V transpose can be filled with any real numbers. Decimals, negatives, whatever the gradient descent finds as it walks down the hill.
Right, it's very fluid.
But what if we put mathematical handcuffs on the algorithm? What if we add a strict rule that says the values in these latent matrices must be binary, only zeros and ones, and they must be completely orthogonal?
We force it to use a very specific set of blocks.
Exactly. When you force the algorithm to only use zeros and ones, and you force the dimensions to be orthogonal, meaning they cannot overlap at all, the continuous, fluid geometric space suddenly collapses. It shatters into discrete, rigid groups.
Okay.
You have literally transformed standard matrix factorization directly into k-means clustering. It's no longer predicting a missing movie rating. It is strictly grouping data points into distinct, non-overlapping clusters based solely on the new rules you gave it.
Wait, so what does this all mean? Are you saying we didn't actually invent dozens of distinct machine learning algorithms, but rather we just discovered different ways to dress up this one single equation with different constraints?
This raises an important question about how we actually teach this stuff. It forces a massive reevaluation of how we conceptualize machine learning. Very often, the field is taught as a fragmented list of isolated tricks. Week 1 is clustering, week 2 is recommenders, week 3 is natural language processing.
Right, like they're completely unrelated subjects.
But this blueprint proves it shouldn't be taught that way. True understanding comes from seeing this one universal factorization tree.
You really do start to see the matrix. Let's bring this all together for you listening. We have taken quite a journey today. We started with the pure mathematical prism of exact SVD, where linear algebra perfectly deconstructs the geometry of a complete spreadsheet.
And then we use the Eckert-Young theorem and the truncation slicer to chop away the noise, filtering for the dominant energy using the Frobenius norm.
Right. Then we hit the wall of extreme sparsity, where pure analytical math failed us, and survived by leaping to stochastic gradient descent, optimizing our way down the topographical map.
And once we made that leap to optimization, a whole new world opened up.
Yeah, we discovered that recommender systems predicting our tastes, word embeddings mapping human language, graph predictions finding our friends, and even k-means clustering grouping our data are all just different branches of the same universal factorization blueprint. You now hold the fundamental key to understanding how modern algorithms actually work under the hood. They aren't magic. or geometry.
It's just elegant, highly optimized geometry.
But I want to leave you with a final thought today, something to really chew on as you go about your week. Think about the glove algorithm mapping the meaning and gender of words. Think about the recommender systems mapping your deeply personal subjective tastes in art and movies. Think about the graph algorithms mapping the social networks of human relationships.
It covers a lot of ground.
If the vast complexity of human language, the intricate social webs we form, and the deeply personal art we love can all be successfully mapped, clustered, and accurately predicted by simply factorizing a sparse matrix, what does that say about the predictability of human nature itself?
That is a big question.
Are our unique, deeply complex human choices, the very things that make us feel like individuals, really just latent vectors waiting to be multiplied? The next time you stare at a massive, messy spreadsheet, ask yourself if you're just looking at a mirror. Thanks for joining us on this deep dive. We'll see you next time.